Greetings, my people. How are we? This is still on 5.3. Remember, there are two different versions, or two different sort of aspects of the fundamental theorem of calculus. Remember, your book actually lists them in the opposite order from what I'm actually saying to you. They call the first fundamental theorem of calculus the fundamental theorem of calculus part 2, and they call this, what we're going to be discussing right now, part 1. But either way, it doesn't really matter as long you're never going to be asked to name them, okay? So as long as you understand both of them, it doesn't matter what you really call them. Just know what I call them and know what your teacher calls them so that you're able to sort of move forward from there. Now, we remember that when we're going through some of this, I was talking about how differentiation and integration are inverses of each other, right? So what happens if we actually want to differentiate an integral? Okay. Well, you're asking yourself, why in the world would you ever want to do that? Well, I got news for you. There are actually applications for it, and the AP test writers love to do this. So they won't give it to you like this. They'll actually give you something like this. They'll give you a function defined as an integral and then ask you to differentiate it. Okay? So all you need to know is that if you're differentiating with respect to x an integral from some number a to x of f of t, it's just f of x. Okay? So we'll sort of, we'll sort of leave that alone right here. Let's go ahead and actually come down here, and I'll explain why this is. And this is why I always do this one second. Well, we don't. This is basically an integral in the abstract, but I can still represent it, right? I can still represent it notationally. So let's actually go ahead and change the form of what's inside here using the first fundamental theorem of calculus. Isn't that it? I mean, isn't that the difference that this integral implies? I've anti-differentiated f and plugged in x and plugged in a and given it as a difference. Okay, well, here's the thing. This right here is variable, right? This right here, because a is a number, is a constant. Okay? So what happens, and now I can, of course, differentiate this difference term by term. What happens when I differentiate f of x, big F of x? It becomes small f of x. And what happens when I differentiate a constant? It becomes 0, and therefore it's just f of x. And that should make sense to us, right? But basically, once we've seen this a couple of times, we go straight from here to here, okay? We know that, for instance, the example that I just gave you, if I have f of x is negative 4 to x of t minus 1 dt, and I want f prime of x, which of course is just small f of x, it winds up being x minus 1. Okay? Now, could you do it the long way? Could you go ahead and, do the integration and make this 1/2 t squared minus t from negative 4 to x? Yes, you could. And then plug it in and get the expression and then take the derivative. But guess what? You're going to wind up right back here at x minus 1. Okay? All you need to know for the second fundamental theorem of calculus is that when you're taking the derivative of something like this, and it has to be number to a variable, when you're doing this, it just becomes f of x. Okay, so let's walk through a couple of examples. It won't really be all that difficult. Let's go ahead and do, let's say I have f of x from negative 3 to x of t squared plus 2t plus 3 dt. And I want f prime of x. I want to take the derivative. I'm telling you, it is this easy. Okay. Well, let's throw a wrinkle in there. Okay. Let's say that I have it not from negative 3 to x, but from x to negative 3 of negative x squared minus, sorry. The hard part about making up problems like this off on the fly is that I wind up forgetting that I need to put t in the integrand. Okay? So let's say I have, instead of negative 3 to x, I have x to negative 3. Okay? Well, can I just change the limits of integration, flip the limits of integration, like that? That's exactly what I need to do. I need the a value to be on the bottom. Okay? The a value needs to be on the bottom in order for this all to work, because remember, this top value winds up being the first term in the difference that this implies. All definite integrals imply a difference. Now, of course, this negative cancels out with those negatives, and when I take the derivative of this, I'm going to get x squared plus 4x. And there we go. Okay? Well, let's throw in another wrinkle. Let's say that I have f of x is equal to the integral of negative 1 to x squared of negative 2 plus 2 dt. Ruh-roh. Well, this is different because that's not x anymore. That is now a function in terms of x. Okay? So let's come back to this in just a second. Let's actually figure out, now we talked about the fact that if I take the derivative of a to x of f of t dt, that winds up being f of x. But what is it when I have the integral from a to u of x, right? U of x is just our catch-all notation for a function or an expression in terms of x, which is just not x in itself. Well, let's go through it the long way, and then we'll figure out what the short way is, okay? Let's go ahead, and that winds up being f of u of x minus f of a, right? That is the difference that implies. Okay, well, now when I differentiate term by term, what's the derivative? Oh, we already know the derivative of that. That's a constant. The derivative of that is 0. What's the derivative of that? Well, it's f of u of x, or times u prime of x. I have to do the chain rule. Okay? So the only difference, if it's a to u of x instead of a to x, is the fact that you go ahead and plug in the u of x, just like you plugged in the x right here for t. X went in for t, and it wound up here. U of x goes in for t, and it winds up here. The only difference is that you then have to tack on a u prime. So you have to do the chain rule, okay? So if we wind up down here, so I go ahead and say, well, f prime of x, I'm going to go ahead and plug in x squared for t. So I wind up getting negative 2x squared plus 2. I then have to tack on the derivative of that expression times 2x. And then, of course, I can simplify. And I get negative 4x cubed plus 4x. Okay, and that should be a 4. I started out doing a 2, but that should be a 4 right there. Okay? Okay, well, let's do a couple of more. Now that we sort of have a beat on it. Yeah, so the AP writers, they love making... They love writing functions defined as integrals. So we're going to have to, you're going to have to know this. And you're going to have to understand exactly what's going on. Okay, well, I'll just go ahead and make one up off the top of my head. Let's do, x to sine x of, let's do f of x is equal to x to sine x of t squared plus t dt. Well, that's different again, because it's not a to u, it's x to u. Okay, so how am I going to do that? Well, I have to do two things. First of all, let's go ahead and let's actually look at it like this first. Let's do it 3 to sine x. Okay? Well, 3 to sine x, I know that sine x is going to go in here, and I'm going to get sine squared x plus sine x. That's my f of u of x. And then I have to take the derivative of that times cosine x. Okay? Well, sorry, that isn't that. That becomes that. That's f prime of x. Okay? So what happens if instead of 3 to sine x, it's x to sine x of t squared plus t dt? Well, I have to split it up. If I have x and sine x, if those represent values, I have to know that there is some constant between them. And that constant between them we'll call a, or we'll call it c. Yeah, we'll call it c. It doesn't really matter what you call it. You can call it k, you can call it whatever you want. T squared plus t dt plus c to sine x t squared plus t dt. Well, this right here winds up being differentiated exactly the way that this one is. Instead of 3, you have c. Well, it doesn't really matter. It's a constant, so when you differentiate it, it goes away. This one, however, needs to be flipped around so that it's c to x of t squared plus t dt plus c to sine x t squared plus t dt. And then when I take the derivative of this, I wind up getting what? Well, it becomes negative x squared plus x plus, and then of course, like I said, this right here is exactly the same as this. It's just a different constant, but who cares? So it winds up being sine squared x plus sine x times cosine x. And that is the derivative of that function defined as an integral. Fun, huh? I knew that you would like it. I knew that you'd be a fan. That's why we went ahead and did it. Let's go ahead and call it quits on this particular video. I will go ahead and get some juicy problems for the next video, and we'll run through all the different varieties as well, and hopefully it'll all solidify by the end of this next video. Bye.